The four-speed transmission has changed very little from 1936 to 1984, with the exception of the shifting mechanisms. There are three different styles of shift mechanisms. The hand shift model, which was in service from 1936 to 1952, the ratchet shifter, which was in service from 1953 to 1979, and the flat plate shifter, which was used from 1980 to 1984. The video you are about to see covers the ratchet top four-speed that was in service from 1953 to 1979. Although the shift mechanisms have changed, the internal workings of all factory four-speeds are similar. Using 5/32 Allen socket, we remove the 12 screws that are securing the top cover onto the transmission case. Notice that there is a vented screw installed on the starter side of the transmission cover closest to this dowel pin. This is to relieve the pressure that is built up inside the transmission when the temperature in the transmission rises. The shift cover is aligned with two dowel pins, which sometimes makes it difficult to remove. If necessary, we use a soft mallet to break the cover seal. Do not use a screwdriver or a pry bar to remove the transmission cover, as this may damage the gasket surface and cause a potential leak. Next, we remove and discard the old shift cover gasket. Using a chisel or a punch, we flatten the lock tab on the cam follower retaining washer. Now, using a 7/8" wrench, we break the torque on the cam follower retaining nut. We back the nut the rest of the way out and remove the lock washer. Inside the cam follower retaining nut, we have a spring and the cam follower itself. Now, using a 5/8" socket, we remove the neutral indicator and the fiber washer. The fiber washer must be discarded. It is not reusable. Next, using an 1/8" Allen wrench, we remove the three countersunk screws from the shifter lever and dust shield. Now, we remove the shift lever and dust shield from the Paul carrier. Now, using a 3/8" wrench and 1/8" Allen, we remove this nut from behind the adapter plate. Out of the 6 Paul carrier screws, this is the only one that has a nut attached. Now, we remove the remaining 5 Allen screws. The Paul carrier cover and gasket are now free to be removed. Next, using a Phillips head screwdriver, we remove the Paul spring retaining plate and the 2 Paul springs. Now, we carefully pull the Paul carrier away from the adapter plate. Looking inside the Paul carrier, we have the 2 shifter pawls. We gently slide the shifter pawls out of their grooves. You must wear approved safety glasses to proceed any farther. The Paul carrier springs are under a bit of pressure and may fly off in any direction. Using a flathead screwdriver or scribe, we carefully pry the springs out of the spring grooves. We quickly inspect both the Paul springs and the Paul carrier springs for signs of damage and/or rust. If any signs of damage exist, the springs must be replaced. Next, using a flathead screwdriver, we remove the screw and star washer from the adapter plate. We then remove the adapter plate and gasket from the shifter cover. Now, using a small flathead screwdriver, we remove the shift drum shaft lock screw. From the primary side of the shift cover, we use a thin punch and hammer to drive the shift drum shaft through the cover. Now, we remove and discard the shifter shaft oil seal. It is not reusable. Next, we lift the shift drum up and out of the shifter cover. Now, using a pair of needle nose pliers, we remove the cotter pin from the end of the shifter shaft. We then slide the shifter shaft out of the cover. The spring and gear can sometimes be difficult to remove. Using a small flathead screwdriver, we gently compress the spring and remove the gear and spring from the cover. Next, using a flathead screwdriver, we remove the screw from the speedometer drive gear assembly. Now, we remove the drive gear assembly and discard the drive gear gasket. Using a 9/16" open-end wrench, we remove the bolt, washer, and lock washer from the kicker pedal. Now, we remove the kicker pedal and spring clip. Now, using 2 9/16" wrenches, we remove the nut, bolt, flat washer, and lock washers from the kicker arm. Now we slide the kicker arm off of the kicker shaft. Next, we rotate the kicker spring slightly clockwise to release the hook from the spring stud. Now we remove the kicker spring from its shaft. Now, using a 1/4 inch Allen socket, we remove the 9 screws from the kicker cover. As we pull the cover away from the transmission, the clutch release bearings or throwout bearing may come away with the cover. On the 1975 and earlier kickstart models, the throwout bearing may look something like this. There is no disassembly necessary for this type of throwout bearing. The 75 and later throwout bearing has a 3-piece bearing and an oil slinger, which are attached to the clutch push rod by this circlip. Using a pair of needle nose pliers, we remove the circlip from the end of the clutch push rod. Now we remove the thrust washer, the linear bearing, another thrust washer, and the oil slinger. We quickly inspect the bearing and the thrust washers for damage. If damage exists, the bearing and thrust washers must all be replaced at the same time. Next, using a punch or chisel, we flatten the lock tab under the starter gear nut. To prevent the starter gear from rotating, we temporarily install the kicker arm onto the kicker shaft. Using a 3/4 inch box end wrench, we remove the nut and lock washer from the end of the kicker shaft. Now we slide the starter gear and the kicker arm off of the shaft. We then remove the shaft and thrust washer from the kicker cover. Next, using a pair of needle nose pliers, we remove the E-clip from the end of the clutch release lever shaft. As we pull the clutch release lever shaft through the top of the kicker cover, the release finger and washers will fall free of the shaft. Now, we remove the finger and washer from inside the kicker cover. Using a punch or a chisel, we flatten the lock tab under the sprocket shaft nut. Next, we slide the main shaft shift clutch into 4th gear. We then slide the counter shaft shift clutch into 2nd gear. This will set the transmission in a locked gear position and prevent the 2 shafts from rotating. To remove the sprocket nut, we are using a sprocket nut removal tool which was provided by Jim's. We thread the pilot onto the end of the main shaft in a counterclockwise direction. Now we slide the removal tool onto the sprocket nut. The sprocket nut has left-hand threads, meaning that we must turn the nut clockwise to loosen. Do not mistakenly turn the nut counterclockwise, as this will damage the threads on the main drive gear. After we've loosened the nut sufficiently, we remove the nut, lock washer, and sprocket from the main drive gear. On some of the earlier models, there is a small L key that must be removed from between the splines of the main drive gear and the main drive gear spacer. While we still have the transmission shafts locked in place, we need to remove the starter clutch nut and counter shaft nut. Using a punch or a chisel, we flatten the lock tab on both the starter clutch and counter shaft lock washers. Next, using a 1-inch socket, we remove the starter clutch nut and lock washer from the end of the main shaft. Then using a 15/16 socket, we remove the counter shaft nut and lock washer. The starter clutch is mounted on a tapered shaft and must be removed using a gear puller. We attach the prongs of the gear puller between the starter main shaft gear and the starter clutch spring. We then install the main shaft protector in the end of the main shaft. Now we tighten the adjuster nut, making sure that the gear puller remains firmly in place. We continue to tighten the adjuster nut until the starter clutch and the starter main shaft gear break free. Next, we remove the starter clutch key using a scribe or needle nose pliers. Now, we remove the starter clutch gear and clutch spring from the main shaft. Next, using an impact wrench, we loosen the 4 screws on the bearing retainer plate. Then, using a flathead screwdriver, we remove the screws and the bearing retainer from the case. From the kickstart side of the transmission, we locate the shift fork shaft lock screw. Using a small flathead screwdriver, we remove the lock screw from the transmission case. With a long, thin punch or drift, we drive the shifter fork shaft through the transmission case. Now, we remove each shifter fork from its respective gear cluster. Next, we place the shift forks in the soft jaws of a vise. Using a punch or a chisel, we flatten the lock tab on the lock washer. Using a 3/4 inch socket, we remove the shift fork nut, lock washer, and any spacers that may have been used during previous installations. Now we remove the shift fork and the remaining spacers from the shift fork bushing. The remaining shift fork is disassembled in the exact same fashion. Now we locate the countershaft lock plate on the kicker side of the transmission. We remove the lock plate, then we gently tap the end of the countershaft to break the shaft free. Now, using a soft punch or drift, we gently tap the countershaft through the gear cluster and out of the transmission. Next, we grab the center of the gear cluster and carefully pull the entire countershaft assembly out of the case. Now, we retrieve the countershaft spacer from the transmission case. From the primary side of the countershaft gear, we remove the thrust washer and the loose rollers from the inside of the gear cluster. For visual purposes, we are using a magnet to retrieve the rollers. Behind the roller bearings, we have another retaining washer and a snap ring. Do not attempt to remove this inner snap ring unless it is damaged. On the kicker side of the gear cluster, we have only to remove the roller bearings and the retaining washer. If disassembling a 1976 or later model transmission, the countershaft may be equipped with caged needle bearings, such as this one here. These are pressed fit and should not be removed unless they are damaged. To check for damage, simply run your finger around the inside of the bearing. If any grinding or damage is felt, the caged rollers must be replaced. Now we are ready to disassemble and inspect the countershaft gear cluster. First, we have the largest gear, which is low gear or first gear. First gear simply slides off the splines along with its bushing and thrust washer. Next, we remove the first and second gear shift clutch. We quickly inspect the shift dogs for rounded edges and or damage. If damage or wear exists, the clutch must be replaced. Second gear is secured to the shaft by a snap ring. Using a small flathead screwdriver and a scribe, we spread the snap ring sufficiently to clear the splines and slide it off the shaft. The snap ring must be discarded. It is not reusable. Following the snap ring, we have second gear. We remove second gear with its bushing and thrust washer. The two remaining gears are machined as one piece and do not come apart. The smaller of the two gears is fourth gear, and the larger gear is third. The middle gear is the speedometer drive gear. Do not remove this gear unless the gear is damaged. While holding the transmission securely, we strike the primary side of the main shaft with a soft mallet. Notice that as we drive the shaft through the case that the main shaft gear cluster is pushing the main shaft race and bearing out as an assembly. Once the main shaft breaks free, do not try driving the shaft any farther. On a stock case, there is a boss right in this area here that interferes with third gear and prevents the shaft from being driven out any further. We must remove the third gear snap ring in order to slide the main shaft the rest of the way out of the case. Using a flathead screwdriver and a scribe, we spread the third gear snap ring and slide it onto the splines. The third gear snap ring will be destroyed as it is removed and must be discarded. As we slide the main shaft from the case, we leave behind the shift clutch, the third gear snap ring, the thrust washer, and third gear. After removing these from the case, we are left with only the main drive gear. While supporting the main drive gear, we tap the gear through the case using a soft mallet. On 1977 and earlier models, the roller bearings are loose in the case and are free to fall out once the main drive gear is removed. We remove the rollers, being careful not to misplace any. On the 1977 and later models, the main drive gear bearing is a cage type, which must be pressed from the case. To remove this type of bearing, we place the case on the press with the primary side facing up. We are using an arbor that is just large enough to contact the bearing but will not interfere with the outer race. Since there is no shoulder on the race, this type of bearing can be pressed directly through to the inside of the case. Next, we place the main shaft assembly in the soft jaws of a vise, being careful not to damage the splines or the bearing surface. Now, using a punch or a drift, we flatten the tab on the lock washer. Using an 1 3/8 deep well socket, we break loose the main shaft bearing nut. We then remove the nut and lock washer from the main shaft. To disassemble the rest of the main shaft, we must press the shaft out of the enclosed bearing and gear cluster. We set the main shaft in the press with bearing supports under the first and second gear cluster. We then place a soft aluminum arbor on the main shaft to protect the shaft tip and threads. While supporting the main shaft, we press the shaft through the bearing assembly and out the bottom of the press. Next, we simply press the main shaft bearing out of its race by hand. It is not necessary to remove the bearing unless the bearing is damaged. Now we place the transmission case on the press with the primary side facing down. We put our arbor into the transmission and position it squarely on the main drive gear seal. We must make sure that the arbor does not interfere with the inside diameter of the main drive gear race. We carefully press the seal and the main drive gear spacer from the case. The main drive gear spacer can now be removed from the main drive gear oil seal. The oil seal must be discarded. It is not reusable. Before we go any further, we quickly inspect the old main drive gear race for pitting and/or grooves. If damage exists, the race must be replaced. If the old race is in acceptable condition, we must check the main drive gear bearing clearance to see if the race is worn beyond the specified tolerances. Using our 1 to 2 inch outside micrometer, we measure the bearing surface of the main drive gear. Our measurement comes to 1 inch, 629 thousandths. Now, using our 0 to 1 inch outside micrometer, we measure the thickness of one roller bearing. Our measurement comes to 125 thousandths of an inch, which is a standard sized roller. We then multiply this measurement by 2, giving us 250 thousandths of an inch. Anytime you measure a loose roller bearing, the measurement must be multiplied by 2. To understand this, you must realize that the bearings take up equal amounts of space around the entire circumference of the race. Next, we add our main drive gear bearing surface measurement and the diameter of the 2 needle bearings, which give us 1 inch, 879 thousandths. Now, to get the overall bearing clearance, we zero our dial bore gauge at 1 inch, 879 thousandths. We then insert the dial bore gauge into the main drive gear race and locate the largest point. This will give us the measured clearance for the main drive gear. The factory specifies that the bearing clearance should be between 5/10 thousandths and 2 thousandths of an inch. If the measured bearing clearance is greater than 2 thousandths of an inch, we have 2 options. We can either use oversized roller bearings or we can replace the race. The oversized rollers can be purchased in 4/10 thousandths, 8/10 thousandths, and 1 thousandths of an inch oversizes. We've developed this chart to help you choose the correct size roller bearing for your transmission. Just as an example, if you had measured 2.5 thousandths of bearing clearance, we would use an 8/10 thousandths oversized roller bearing, and this would bring your measured clearance to approximately 9/10 thousandths of an inch. If the bearing clearance on the old race is larger than 3.5 thousandths of an inch, then oversized bearings will not work and the main drive gear race must be replaced. To remove the old main gear race, we must first remove this retaining ring from the inside of the transmission case. Using a scribe, we pry the retaining ring out of its groove and discard it. We place the transmission case in the press with the primary side facing down. Now we place the arbor squarely on the race and carefully press the race from the transmission. Using our free hand, we support the race as it breaks free. Notice that the main drive gear bearing race has a retaining ring groove cut into one side and a shoulder machined into the other side. We place the new bearing race in its bore with the retaining ring groove facing towards the inside of the case. We place the arbor squarely on the race and carefully press the race until it is seated firmly on the outer shoulder. We then install the new race retaining ring in its respective groove on the inside of the main drive gear race. Before measuring the new race for the proper clearance, the race must first be straightened with the line lapping tool. Essentially, what we are doing is making sure that the main drive gear race and the main shaft bearing are perfectly aligned with one another. We must install the main shaft bearing and race temporarily to complete the line lapping procedure. We set the transmission case in the press with the primary side facing down. We then put the main shaft bearing race in position with the outer shoulder facing up. Using an arbor large enough to cover the outer shoulder, we press the race into the transmission until the shoulder sets firmly against the surface of the case. Next, we put the main shaft bearing into position and carefully press it into the race until it sets firmly against the inner shoulder. The line lapping tool we are using was supplied to us by Jim's. This is a precision machine pilot which comes with the line lapping tool. We install the pilot inside the main shaft bearing. The clearance will be a little tight, so we will tap the pilot in place using a soft blow hammer. For a little added stability, we are placing the transmission case in a fixture to hold it securely in the vise. Using a 9/16 open-end wrench, we install the nuts on the fixture and tighten them snugly. We then install the case in the vise. Next, we apply a liberal coating of 220 grit lapping compound to the outside surface of the mandrel. We then slide the lapping tool through the main drive gear race and into the pilot. Using a variable speed drill motor on a relatively low speed, we lap the inside of the race, frequently cleaning and inspecting the race for uneven areas. The lap surface will take on a dull shine. Areas on the race that are not being touched by the lapping tool will remain shiny. This is an indication that the race is not yet straight. We continue to lap the race until the entire surface is the same dull color. At this point, our race is straight. Next, we zero our dial bore gauge to the combined diameters of the main drive gear bearing surface, 1 inch 629 thousandths, and the two 125 thousandths roller bearings, giving us a total of 1 inch 879 thousandths of an inch. Now, we insert our dial bore gauge into the main drive gear race. Our dial is reading plus 3/10 thousandths of an inch, giving us a diameter of 1 inch 879 thousandths and 3/10, or a clearance of 3/10 thousandths. The clearance we want is 5/10 thousandths of an inch, or a diameter of 1 inch 879 thousandths and 5/10. We keep lapping and measuring our race until our dial is reading a uniform plus 5/10 thousandths of an inch up and down our race, giving us an overall inside diameter of 1 inch 879 thousandths and 5/10. For the complete procedure for determining the main drive gear bearing size and clearance, please refer to the main drive gear bearing clearance section in this video. The countershaft races are not a common replaced item due to the fact that the countershaft does not rotate. The only part of the countershaft race that may show excessive wear is this outer shoulder. A new race will have 2 deep oil grooves cut into the shoulder. As the race wears, the grooves will become noticeably thinner, thus causing more countershaft end play. If the largest countershaft shim will not bring the end play within the specified tolerance, then the race must be replaced. To remove the old countershaft races, we place the transmission in the press with the primary side facing down. We place our arbor squarely onto the kicker side race and press towards the interior of the case. We use our free hand to catch the race as it breaks free. Now, we flip the transmission over so that the kicker side is facing down. Again, using the arbor, we press the primary side race towards the interior of the case. Notice that one of our countershaft races has a shoulder machined into the inner diameter. This race is installed into the kicker side of the transmission. This other race has an outer shoulder but no inner shoulder. This race is installed into the primary side of the transmission. We place the transmission case in the press with the primary side facing down. The race with the large inside diameter and no inner shoulder must be installed first. We place the race in the bore with the outer shoulder facing up. Placing the arbor squarely on the race, we press the race in until the shoulder seats firmly on the case. Now we flip the transmission case over so that the kicker side is facing down. We place the countershaft race in the case with its outer shoulder facing up. We then insert the arbor into the race and up against its inner shoulder. Now we carefully press it in until its outer shoulder sets firmly on the case. If you ever find yourself in a situation where you need to identify the year and model of a 4-speed transmission case, there are several distinct features that apply only to certain years. The cases from 1965 and earlier are easy to spot because they are designed with no tab supports for the inner primary. This was prior to the introduction of the first starter model. Therefore, the inner primary supports were not necessary. The case we're using for this particular transmission build is from Cal Products. This style of case would cover the electric start models from 1965 to 1976. One of the identifying features for this year and model is, of course, the tab supports for the inner primary. The second identifying feature is that this case has a large main drive gear bore. The bore measures approximately 2 inches, 310 thousandths. The larger bore is designed to accept the early style race and loose roller bearings. This next case also has the tabs for the inner primary, but as you can see, the bore for the main drive gear is much smaller. This bore measures approximately 2 inches in diameter. The smaller bore accepts the newer style of caged roller bearings. This type of case was only in service from 1977 to 1979. In late 1979 to early 1984, the factory changed the case styles again, but kept the caged rollers. This case is easy to distinguish from the earlier style 4-speeds because of the noticeable difference in shape. This type of case was designed to accept a totally different style of shifter assembly called the flat plate shifter. This next case is in a class all its own. This is a Sputh case, which is designed to accept a complete set of Evolution-style 5-speed gears, yet it still fits in the 1984 and earlier 4-speed frames. This is one of the more popular conversions being performed by bike builders today. If you're interested in this type of project, refer to our video manual's 5-speed transmission tape. Now we need to check the clearance between the main shaft and the main drive gear bushing. Using a small snap gauge and a 1 to 2 inch outside micrometer, we measure the inside diameter of the main drive gear bushing. Our measurement comes to 1 inch and 2 thousandths. Using a 1 to 2 inch outside micrometer, we measure the bearing surface of the main shaft in several places. Our measurement comes to 1 inch. Now, we subtract 1 inch from 1 inch and 2 thousandths. This gives us a clearance of 2 thousandths of an inch. Factory specifications are from 1 thousandths and 8 tenths to 3 thousandths and 2 tenths of clearance. So we are well within tolerance. If the clearance is greater than 3 thousandths and 2 tenths, we will need to replace the main drive gear bushing. To replace the main drive gear bushing, we place the main drive gear in the press with the gear side facing down. We are using a special bushing driver which is supplied by Jim's. The driver slides into the main drive gear until this shoulder contacts the bushing. We place the tool on the edge of the bushing and carefully press it through the main drive gear. With our free hand, we support the bushing as it breaks free. The main drive gear bushing has oil grooves which are directional. On one side, the grooves come all the way to the edge of the bushing. This side always faces the inside of the transmission. On the other side, the oil grooves come close to the edge but not quite touching the edge. This side always faces towards the primary side. Once the new bushing is properly in position, we slide the sleeve over the bushing. This sleeve ensures that the bushing will automatically be set to the proper depth. The outer edge of the bushing should set approximately 50 thousandths of an inch below the groove where the main drive gear seal sets. First, we apply some grease to the bearing race to hold the bearing in place. Apply the grease over the entire surface of the race. Carefully, we lay each of the bearings side by side along the inner surface of the race. The grease will keep the rollers from sliding around. Make sure that all of the bearings remain firmly in place. Then apply another coating of grease over the bearings to help keep them in position. The main drive gear thrust washer is approximately 2 inches in diameter and can be installed in either direction. Now we place the main drive gear thrust washer over the bearings from the inside of the case. This will help us guide the main drive gear through the race without disturbing the rollers. There are 2 different types of main drive gear oil seals. One type has a metal outer ring, and the other type is made of a synthetic rubber. They both need to set flush with the outer surface of the gear. Next, we place the main drive gear seal over the main drive gear and press it in place. The seal should set flush with the outside surface of the gear. Now, we carefully slide the main drive gear through from the inside of the case, making sure that we don't disturb any of the loose bearings. To keep the bearings stationary while we are installing the main shaft, we need to install the main drive gear spacer and the main drive gear oil seal. We're using a double-lipped main drive gear seal from James Gaskets. This seal provides a little added protection against potential leaks. As you can see, on one side of the seal, the lip comes all the way to the outer edge. This is the front of the seal, which always faces away from the transmission. On the other side, there is a gap between the metal case and the rubber lip. This is the back side of the seal, which always faces the main drive gear spacer and the main drive gear. We apply a liberal coating of grease to the main drive gear spacer. We then install the spacer through the back side of the seal, making sure that the lip of the seal doesn't fold over. Now we put the oil seal cork washer in place over the main drive gear. Next, we put the seal and the main drive gear spacer in place over the main drive gear. We then place the transmission in the press, making sure that we keep the main drive gear firmly in place. Now we place the arbor squarely over the seal and press it in place. The seal should set flush with the outer surface of the case. These are Andrews replacement main shafts for all versions of the Big Twin 4-speed transmission from 1937 to 1984. This shorter main shaft replaces the factory main shaft from 1937 to 1964. The next main shaft replaces the first electric start models produced from 1965 to 1969. This one is a replacement for the shaft produced from 1970 to 1984. And the last 4-speed main shaft is for the 1984 and 1985 belt drive models. All of the Andrews main shafts are made from aircraft alloy steel, which is heat-treated and ground finished to ensure maximum durability. Before we begin assembling the main shaft, we quickly inspect our old shaft for grooves, pitting, or damage. If damage exists, the main shaft must be replaced. The main shaft gear cluster is comprised of 2 gears and has an internal spline. The smaller of the 2 gears is first gear, and the larger gear is second gear. We set the main shaft gear cluster in the press with first gear or the smaller of the 2 gears facing down. Notice that the kicker side of the main shaft has a tapered end with 2 separate sets of threads. We slide the kicker side of the main shaft down into the low gear cluster, making sure that the gear teeth mesh together with the splines on the shaft. Next, we place the main shaft bearing retainer on the press with the cup side facing up. We then place the main shaft bearing squarely on the retainer. The arbor we use must support the outer race of the bearing. With our arbor in place, we press the bearing into the retainer until it sets firmly on the shoulder. Now, we place the bearing and retainer in the press with the bearing cup facing down. We then insert the main shaft into the bearing inner race. We press the main shaft into the bearing, making sure it sets firmly against the shoulder on the low gear cluster. Spin the bearing on its shaft to make sure it rotates freely. Main shaft third gear has a large shoulder machined onto the kicker side of the gear and 6 shifter slots machined into the side that faces the main drive gear. From the kicker side of the transmission, we insert the main shaft into the case. We slide third gear on the main shaft with the shifter slots facing towards the main drive gear. The third gear thrust washer for the main shaft has two inner tabs and measures approximately 1.5 inches across. This is the third gear snap ring. It measures approximately 1.25 inches across. We slide the third gear thrust washer and the third gear snap ring onto the main shaft. The third and fourth gear shift clutch is directional. The factory shift clutch will have the word high stamped on one side of the gear. The word high always faces towards the main drive gear. The shift clutch we are using is an Andrews shift clutch. In place of the word high, Andrews has stamped AP4 on the same side that faces the main drive gear. After we get the shift clutch into position, we slide the main shaft into the main drive gear. It may be necessary to slide third gear and the third gear snap ring up onto the splines in order to get the main shaft into position. Using a flathead screwdriver or a scribe, we work the snap ring along the splines and into the snap ring groove. As we rotate the main shaft, check to make sure that the snap ring is set firmly in its groove. Next, we slide the main shaft shift clutch up onto the splines. Now we slide the main shaft into the main drive gear. The main shaft bearing will prevent us from inserting it all the way into the case. Once again, we place the transmission onto the press with the main drive gear facing down. For a little added precaution, we slide the shift clutch up onto the main shaft. This is to ensure that when we press the bearing into place, the shift clutch does not interfere with the splines on the main shaft. We place the arbor squarely against the bearing's outer race. Carefully, we press the bearing into the case until the shoulder on the bearing retainer butts up firmly against the case. The bearing lock plate must be positioned so that the angled cutaway faces towards the counter shaft. Using some medium-strength locking compound and a flathead screwdriver, we install the 4 countersunk screws into the bearing lock plate. To install the speedometer drive gear on the countershaft gear cluster, we place the drive gear on the press, making sure that the outer diameter of the gear is supported completely. We must make sure that fourth gear, or the smaller gear, can pass safely through the speedometer drive gear without contacting the supports. The countershaft gear cluster has third and fourth gears permanently attached to a spline shaft. We place the countershaft gear cluster on the speedometer drive gear and press it in place. The speedometer drive gear does not seat against the shoulder or groove, so we must be careful not to press the gear too far. Before installing the countershaft roller bearings, we must check the bearing clearance. We measure this the same way we measured the bearing clearance on the main drive gear. We measure one roller bearing and multiply that measurement by 2. Our measurement comes to 125 thousandths of an inch, which is a standard roller size. Multiplied by 2, we get 250 thousandths of an inch. Now, using our 0 to 1 inch outside micrometer, we measure several places on the countershaft. Our measurement comes to 755 thousandths and 3/10. Now we add our bearing measurement and our countershaft measurement. We come out with 1 inch, 5 thousandths and 3/10. Next, using a snap gauge and a 1 to 2 inch outside micrometer, we measure the inside diameter of the countershaft gear cluster. Our measurement comes to 1 inch, 6 thousandths and 3/10. Now we subtract 1 inch, 5 thousandths and 3/10 from 1 inch, 6 thousandths and 3/10. This gives us an overall bearing clearance of 1 thousandths of an inch. The factory specifications are between 5/10 thousandths of an inch and 2 thousandths of an inch, so we are well within tolerance. Using a small pair of snap ring pliers, we install the 2 bearing retainers, making sure that they snap firmly in place. There are 2 snap ring grooves, one in each side of the countershaft gear cluster. The countershaft first and second gears both have bushing inserts that fit inside the gear. They both simply slide in place, but they are not the same size. The larger of the 2 bushings is for second gear, and the smaller one fits into first gear. We place the countershaft gear cluster on our workbench with fourth gear, the smallest gear, facing down. Countershaft second gear is approximately 2.8 inches and has 5 shifter dogs on the kicker side of the gear. We slide the countershaft second gear with its bushing onto the gear cluster with its shift dogs facing up. The second gear thrust washer is the same shape as the main shaft third gear thrust washer, only it is slightly larger. We slide the thrust washer into place against second gear. The second gear snap ring measures approximately 1 3/4 inches across. Using a scribe or a small flathead screwdriver, we maneuver the second gear snap ring onto the shaft and into the snap ring groove. These two thrust washers are identical in shape and size. There is one for each side of the gear cluster. We place the thrust washer inside the gear cluster, making sure that it sets flush against the snap ring that we installed earlier. Next, we apply a liberal coating of grease to the inside of the bearing race. For visual purposes only, we are using a pair of tweezers to install the bearings. This would normally be accomplished using our fingers. We install the bearings side by side around the inner race. There should be 22 bearings for each side. After the bearings are in place, we install the thrust washer in the groove at the end of the gear cluster. Now we flip the gear cluster around and repeat the procedure. First comes the thrust washer, then the grease, then the bearings. This side of the gear cluster is assembled in the same manner, only this side has no outer thrust washer. The countershaft first and second gear shift clutch has no direction. It can be installed either way, and it will work the same. Next, we install the first gear thrust washer. It rests on this shoulder at the end of the spline shaft. The countershaft first gear is the largest of the countershaft gears. It's flat on one side and has 5 shift dogs on the other side. We install the countershaft first gear with its bushing on the end of the shaft. The shift dogs face toward the shift clutch. Harley Davidson has incorporated 3 changes to the 4-speed countershaft since 1941. The first shaft at the top of your screen was used on the loose roller bearing models from 1941 to early 1976. The second shaft covers the caged bearing models from late 1976 to 1979. This groove on the kicker side of the shaft is for identification purposes only. The last shaft is for the late model 4-speed from 1980 to 1985. In this particular transmission, we will be using the shaft from 1941 to 1976, which is easily identified by its single groove. To check the countershaft end play, we place the countershaft gear cluster in the transmission with 4th gear, the smallest gear, facing the primary side. Now we slide the countershaft through the gear cluster about 3/4 of the way in. We need to leave just enough room to install the countershaft spacer. We turn the transmission up on its side with the primary side facing down. Now we insert the countershaft spacer on top of the gear cluster so that the hole in the spacer lines up with the shaft. These shims come in different sizes ranging from 74 thousandths to 120 thousandths of an inch. We're inserting a shim that measures 100 thousandths of an inch. As we slide the shim in place, we need to make sure that the hole in the shim lines up perfectly with the countershaft. Now we slide the countershaft the rest of the way through the case. We lay the transmission flat on the bench and slide the gear cluster back as far as it will go. Now we insert the feeler gauge between the spacer and countershaft first gear. The factory specifications are between 4 thousandths and 12 thousandths of an inch. Ideally, the end play should be around 5 thousandths. We continue inserting various sized shims until we've obtained a clearance of around 5 thousandths of an inch. If the countershaft end play cannot be brought within the specified tolerance by using the largest shim of 120 thousandths, then this is an indication that the shoulder on one or both of the countershaft races has worn thin and must be replaced. Refer to the countershaft race removal and installation section that we covered earlier. Before installing the countershaft permanently into the case, we must place the new O-ring into the groove provided on the primary side of the shaft. Make sure, before tapping the countershaft all the way through the case, that this flat cutaway on the kicker side of the shaft is facing directly away from the main shaft. Now we install the counter shaft lock plate with the flat side flush against the main shaft lock plate. We then install the lock washer and the counter shaft nut. The main shaft nut has a shouldered side and a flat side. The flat side always faces in towards the main shaft bearing. Using a flathead screwdriver or a scribe, we slide the main shaft shift clutch into fourth gear. We then slide the counter shaft shift clutch into second gear. This will lock the shafts together and allow us to torque the main shaft and counter shaft nuts. Using a foot-pound torque wrench, we torque the counter shaft nut from 55 to 65 foot-pounds. We then torque the main shaft nut from 50 to 60 foot-pounds. Now, using a punch or a chisel, we bend the lock tabs on both the counter shaft and main shaft nuts. Before installing the shifter gear into the cover, we need to identify the timing mark on the face of the gear. When installed, the timing mark faces towards the inside of the ratchet cover. For ease of locating the timing mark after the gear is installed, we have placed a mark on the gear that can be seen from above the actual timing mark. When installing the shifter shaft into the shifter gear, we need the timing mark on the gear to line up with this area on the shaft just to the left of the gear teeth. In any other position, it will be noticeably off. Now we place the shifter spring over the hub on the shifter gear. We then place the gear and spring in the shifter cover with the gear's timing mark facing toward the ratchet assembly. For ease of locating the timing mark, we must position the timing mark so that it faces straight up. While holding the gear in position, we slide the shifter shaft through the cover with the timing marks lined up as shown earlier. Now we insert a screwdriver or a punch to press against the gear while we install the cotter pin. After installing the cotter pin, we remove the punch, then rotate the gear around and bend the tabs back with a screwdriver. Make sure that the tabs on the cotter pin do not obstruct the normal rotation of the gear. Before installing the shifter shaft, we need to apply a little assembly lube to the shaft. Then we install the oil seal in the second groove from the end of the shaft. Now we locate the timing marks on both the shifter drum gear and the shifter shaft gear. We place the shift drum into the shift cover with the cam slots facing up. While rotating the shift drum, we visually check that the timing marks on both gears mesh with one another. We then slide the shift shaft through the shift drum with the single groove on the shaft going toward the gear side. The single groove at the end of the shaft needs to line up with the lock screw hole in the cover. When the shaft is installed correctly, the groove on the other end of the shaft will stick out slightly. Now, using a small flathead screwdriver, we install the shifter shaft lock screw. Next, we apply a liberal coating of grease to the cam follower spring. We then slide the spring into the cam retainer. Now we slide the cam follower over the spring. While holding the retaining washer in place on the ratchet cover, we install the cam follower assembly into the cover. Using a 7/8" wrench, we tighten the cam follower. Now we flip the shifter cover over to get a better angle on the lock tab. Using a punch or a chisel, we bend the lock tab down onto the cam follower retainer. Next, we install the fiber washer on the neutral indicator switch. We then install the indicator in the cover. Using a 5/8" wrench, we tighten the neutral indicator. While holding the gasket against the cover, we put the adapter plate in place and install the screw and star washer. Before tightening the screw completely, we will make sure the timing notch on the shifter shaft is aligned with the timing mark on the adapter plate as shown here. At this point, the shift drum can be placed in any gear except neutral. If the shift drum is in the neutral position, the notches cannot be aligned properly. Now, using a flathead screwdriver, we tighten the screw. Next, we apply a liberal coating of grease to the two Paul carrier springs. We then insert the two springs in the grooves in the adapter plate. Now, we install the pawl carrier onto the adapter plate, making sure that the tab fits squarely in the small opening between the two pawl carrier springs. Next, we apply a liberal coating of grease to the two shifter pawl springs and the shifter pawls. Now we flip the cover over and slide the two shifter pawls into the pawl carrier, making sure that the two notches are facing one another. Then we install the two springs into the shifter pawls. Next, we place the spring retaining plate on the pawl carrier. We then install the countersunk screw. Using a Phillips head screwdriver, we tighten the screw. While holding the cover gasket in position, we put the pawl carrier cover in place and install the 5 of the 6 cover screws. We then slide the last screw through the hole at the 6 o'clock position and install the 3/8" nut. This is the only cover screw that has a nut attached. Using an 1/8" Allen and a 3/8" wrench, we tighten the nut and the remaining 5 cover screws. Next, we apply a few drops of medium-strength locking compound to the 3 shift lever screws. While holding the dust cover in position, we put the shift lever in place and install the 3 countersunk screws. Now, using an 1/8" Allen, we tighten the 3 screws. All of the hardware for both the main shaft and counter shaft shift forks are interchangeable except for the shift forks themselves. We will start the assembly by locating one of the shift fingers. The shift finger is shown here with its finger at the 12 o'clock position and a locating detent pin at the 6 o'clock position. This detent pin extends across the bottom of the shift finger to ensure proper alignment of the shift fork bushing and the counter shaft shift fork. Next, we locate the shift fork bushing. As you can see, the shift fork bushing has a groove cut into it which matches the size of the shift finger detent pin. While holding the shift finger straight up and down, we insert the shift fork bushing from the rear, making sure that the shift finger detent pin slides smoothly into the groove. Now we slide the large spacer over the bushing and up against the shift finger. Next, we slide our pre-measured shims over the bushing and up against the spacer. How to determine the required thickness of shims will be shown in the shift fork adjustment section later in the video. Now we locate the counter shaft shift fork, which is the wider of the 2 shift forks. The counter shaft shift fork measures approximately 1.95 inches. The shift fork also has a locating detent pin. The location of this detent pin ensures that the counter shaft shift fork jaws are angled correctly each time they're installed. We flip the counter shaft shift fork over so that its locating detent pin is situated at the 9 o'clock position and its shoulder is to the left. Keeping the shift fork in this position, we slide it on the shift fork bushing so that the jaws are facing to the 3 o'clock position. The lock washer also has a detent pin. As we are installing the lock washer, we must make sure that the detent remains in its groove or it will prevent the shift fork nut from locking down all the way. The shift fork nut has a flat side and a recessed side. The recessed side always faces in towards the lock washer. The recess allows the nut to be drawn down tight against the lock washer and shift fork. Make sure, once the nut is snugged down, that there is no side-to-side play. Now, taking one last look at the order in which the hardware is installed, the pre-measured shims go between the spacer and the shift fork. The lock washer is placed between the shift fork and the nut. Now for the main shaft shift fork. We slide the shift fork bushing into place in the shift finger. Next, we place the large spacer up against the shift finger, followed by our pre-measured shims. Remember, the shim thickness will be determined in the shifter fork adjustment section later in the video. The jaws of the main shaft shift fork measure approximately 1 inch 550 thousandths. The main shaft shift fork also has a locating detent pin. We flip the main shaft shift fork over so that its detent pin is at the 5 o'clock position. While keeping the detent pin at 5 o'clock, we install the shift fork on the bushing. When installed correctly, the main shaft shift fork will tilt slightly to the left. In some cases, we need to install shims under the lock washer to ensure that the shift fork is locked solidly in position. This will be explained in more detail in the shift fork adjustment section. Next, we install the lock washer, followed by the nut. Remember, the detent in the lock washer must remain in its groove or it will prevent the nut from locking down tight. Let's review what we've just done. The shims under the lock washer do not affect the shift fork spacing. They are only here to ensure that the nut draws down tightly against the shift fork. The shims between the spacer and the shift fork are the only ones that affect the shift fork spacing. Once completely assembled, we lay the two shift forks on the bench with the shift fingers pointing to the 12 o'clock position. The jaws of the counter shaft shift fork will be pointing to the 3 o'clock position, and the jaws of the main shaft shift fork will face the 7 o'clock position. The correct adjustment to the shifter forks is crucial for the smooth operation of the transmission. Keep in mind as we assemble the shift forks that this is not the final installation. We will be adding shims to obtain the correct spacing of the shift clutches. We will start by setting up the counter shaft shift fork. While holding the shift finger at the 12 o'clock position, we insert the shift fork bushing. Now we locate the large spacer and slide it in place against the bushing. Next, we slide the counter shaft shift fork on the bushing. The jaws of the shift fork must again face the 3 o'clock position. As we tighten the nut with no shims, we discover that the nut runs out of threads before actually tightening against the shift fork. Therefore, the shift fork is free to move from side to side. To take up this extra space, we are installing 3 shims that measure approximately 45 thousandths of an inch. The shims should set flush against the shift fork. As we install the lock washer, we must again make sure that the detent is lined up properly. The nut needs only to be finger tight at this time, as we will be adding shims as necessary. Make sure once the nut is snug that the shift fork cannot be moved from side to side. Now for the build-up of the main shaft shift fork. First, we insert the shift fork bushing into the shift finger. We then install the large spacer. Now we slide the main shaft shift fork in place on the bushing. Next, we install the assortment of shims and the lock washer onto the shift fork bushing. To complete the assembly, we install the nut over the lock washer and snug it down. Again, make sure that the tab on the lock washer is aligned in its groove and that there is no side-to-side play. After both shift forks are assembled, we double-check to make sure we have the shift forks on the correct way. The counter shaft shift fork is on the left of your screen, and the main shaft shift fork is on the right. Next, we take the smaller shift fork for the main shaft and install it in the shift clutch groove. Then we take the counter shaft shift fork and install it in its groove. The shift fork shaft has 2 grooves cut into it, one wide deep groove and one thin shallow groove. We slide the shaft through the primary side of the case with the wider groove first. It is not necessary to drive the shaft all the way into the case at this time, as we will be removing it in just a second. Now that we have the shift forks installed, we need to set up our shift fork adjustment tool on the shift cover. But first, we will have to set the shift cover into 4th gear. The first notch is for 1st gear. The second notch is for neutral. The third notch is 2nd gear. Next comes 3rd gear, and the last notch is 4th gear. By pushing the shift lever forward, we rotate the shift drum to the last notch, which is 4th gear. Next, we place the GIMS alignment tool on the shifter top with these 2 dowel pin holes aligned with these 2 dowel pins on the tool. For visual purposes, we're going to rotate this cover so you can get a better view. We slide the alignment block on the tool until it lines up with this straight groove in the shift drum. The alignment pin must fit smoothly in both grooves. Now we tighten the alignment block with the thumb screw. Now we rotate the shift drum over to 3rd gear. Again, the straight notch in the shift drum must align with the notch in the alignment block. Now using the thumb screw, we secure the adjustment block in place. Before installing the alignment tool on the transmission case, we must install the shift rollers on the top of the 2 shift fingers. Now, we remove the alignment tool from the shift cover. We flip the tool over and install it upside down on the transmission case, making sure that the shift rollers slide into the grooves in the alignment blocks. The transmission is now in the neutral position. The next step is to measure the spacing on both sides of each shift clutch. Our goal here is to make the proper adjustments to center both the counter shaft and main shaft shift clutches equally between the gears. First, we will check the spacing for the counter shaft shift clutch. Before inserting the feeler gauge, we must press the shift clutch firmly against the shift fork to eliminate all of the side-to-side play in both the shift clutch and the shift fork, thus allowing us to get an accurate measurement. Our measurement comes to 105 thousandths of an inch. Now we insert the feeler gauge on the other side, between counter shaft second gear and the shift clutch. Once again, we must make sure that the shift clutch is pressed up hard against the shift fork in the opposite direction. This measurement comes to 60 thousandths of an inch. We will need to keep an accurate record of each measurement as it's taken. The main drive gear has a tendency to slide in and out of the case if not held firmly in place. To alleviate this problem and to accurately measure the clearance of the main shaft shift clutch, we need to temporarily install the main drive gear sprocket. The main drive gear sprocket nut has a left-hand thread, which means we must tighten the nut in a counterclockwise direction. We then thread the pilot onto the end of the main shaft. It also has a left-hand thread. Next, we install the Jim sprocket nut tool and tighten the nut just enough to take the slack out of the main drive gear. Again, when taking measurements, make sure that the shift clutch is pressed hard up against the main shaft shift fork. We insert the feeler gauge on each side of the shift clutch and record our measurements. Our measurements come to 105 thousandths of an inch on each side of the shift clutch. The factory specs are 100 to 110 thousandths of an inch on each side. So right away we can see that the main shaft shift fork is already centered between its respective gears. For our calculations, we will use the measurements from the counter shaft shift clutch. The factory specifies 80 to 90 thousandths of an inch on each side of the counter shaft shift clutch. So our next step is to calculate how far over we need to move each shift clutch to get it centered within the factory specified tolerance. We take our larger measurement of 105 thousandths and subtract the smaller measurement of 60 thousandths. This gives us 45 thousandths of an inch. Now, to find the thickness of shims needed to center the shift clutch, we simply divide 45 thousandths by 2, which gives us 22.5 thousandths. We round this number off to 23 thousandths of an inch. The two most common shim sizes available in the industry are 7 and 14 thousandths of an inch. The closest we can get with the existing shims is 21 or 28 thousandths of an inch. We will select the closest combination, which is 21 thousandths of an inch. Now, we take our largest measurement of 105 thousandths of an inch and subtract 21 thousandths of an inch. This gives us 84 thousandths of an inch of space between first gear and the counter shaft shift clutch. This brings our shift clutch within 1/1000th of an inch of dead center, which is ideal. Now we have to remove the shifter forks again to install the correct shim packs to center their respective shift clutches. Using the Jim's tool, we loosen and remove the nut, lock washer, and sprocket from the main drive gear. Then we once again remove the shifter shaft and shifter forks from the transmission. Next, we remove the nut, the lock washer, the shims, and the shift fork from the shift fork bushing. We place 3 shims measuring 21 thousandths of an inch flush up against the large spacer. Next, we reassemble the shift forks in the same order as before. Now, we insert our feeler gauge once more to verify that we have achieved the correct shift fork spacing. After the proper spacing has been achieved, we remove the shift fork shaft and place the shift forks gently in a vise. Now we tighten the nuts using a 3/4 inch wrench. Using a punch or a chisel, we bend one lock tab up on each shift fork nut. Next, for the final assembly, we install the flat O-ring on the shift fork shaft. We then place the 2 shift forks in place and drive the shift fork shaft into the case until the groove for the lock screw is visible through the lock screw hole. Now, using a small flathead screwdriver, we install the shift fork shaft lock screw. Before we assemble the kickstart cover, we need to install the main shaft kickstart gear and clutch. First, we place the starter clutch spring over the end of the main shaft. We then lubricate the inside of the starter gear. With the clutch teeth facing out, we slide the gear in place on the main shaft. Next, we put the key in place on the main shaft, making sure it sets squarely in the groove. We slide the starter clutch on the shaft with its teeth facing the starter gear. The groove in the gear must align with the key on the main shaft. This is a taper fit, so the starter clutch will not go all the way on until we torque the nut. Next comes the lock washer. The lock washer also has a tab that must be aligned in the keyway groove. Now we install the nut onto the end of the main shaft. Before tightening the nut, we will need to slide the main shaft and counter shaft shift clutches into gear to prevent the main shaft from rotating. Using a 1-inch socket and a foot-pound torque wrench, we tighten the starter clutch nut from 50 to 60 foot-pounds. Now, using a chisel or a punch, we bend the lock washer over onto the starter clutch nut. Next, we will install the starter crank stop. We apply a few drops of medium-strength locking compound to the threads of the screws. Now, using an impact driver, we tighten the 2 screws. Next, we slide the clutch release lever shaft part way through the top of the kicker cover. While holding the clutch release finger in place at a 90-degree angle to the kicker cover, we slide the release lever shaft first through the square on the release finger, then through the thrust washer. Using a pair of needle nose pliers, we install the E-clip on the bottom of the release lever shaft. Before installing the kicker shaft into the cover, we apply a little assembly lube to the outside of the shaft and to the inside of the bushing and O-ring. The washer has a chamfered side and a flat side. The chamfered side faces out towards the kicker pedal. We slide the shaft into the cover until it sets firmly in place. Now we rotate the shaft so that the slot in the shaft is at the 8 o'clock position. Now we turn the cover over and install the starter gear so that the gear stop is around the 8 o'clock position. Next, we install the lock washer and the nut onto the end of the kicker shaft. To keep the shaft from rotating when we tighten the nut, we temporarily install the kicker arm to use for leverage. While holding the kicker cover in place, we use a foot-pound torque wrench to tighten the starter crank nut from 50 to 60 foot-pounds. Using a flathead screwdriver, we bend the tab on the lock washer over onto the starter crank nut. Now, using a 7/16 inch wrench, we install the starter spring stud in the outside of the kicker cover. Next, if we are using a late model throwout bearing, we place the oil slinger on the end of the clutch push rod. The cup side of the oil slinger faces inward. Now we install one thrust washer, then the wafer bearing, and then another thrust washer. Now we install the E-clip in the groove at the end of the shaft. We then apply a light coating of assembly lube to the push rod and slide it into the main shaft. Before installing the kicker cover, we need to make sure that the stop on the starter gear is situated in around the 8 o'clock position. When we install the kicker cover, we must make sure that the gear stop rests against the flat side of the crank stop right in this area here. Next, we install the kicker cover gasket on the kicker cover and install a bolt or two to hold the gasket in place. The factory cases are equipped with studs that are already installed in the case, so this may not apply. We then place the kicker cover on the case, making sure that the clutch finger sets flush against the throwout bearing. Using a 1/4-inch Allen socket and a torque wrench, we install the 9 Allen bolts in the cover using the cross pattern method. We tighten the bolts or nuts, whichever the case may be, from 13 to 16 foot-pounds. Now we put the kicker spring on the kicker shaft, making sure that the straight tab on the spring slides into the notch in the shaft. We then rotate the spring clockwise and hook the spring around the spring stud. Next, we install the bushing in the kicker pedal. We then place the tension spring on the pedal with the flat side facing in. Now we slide the pedal into the kicker arm until the holes line up. Now we install the thrust washer, lock washer, and the bolt into the kicker arm. Using a 9/16 inch wrench, we tighten the bolt good and tight. We place the kicker arm on the kicker shaft at the 12 o'clock position. Now we install the bolt and washer into the kicker arm. Next, we install another plain washer, the lock washer, and the nut. Using a 9/16 inch wrench, we tighten the nut. Before we go any farther, we must check the kickstarter to make sure it operates properly. We slide the shift clutches into the neutral position. Then, while holding the transmission firmly in place, we actuate the kicker arm. Make sure that it springs back and that it returns to the 12 o'clock position. Now we install the gasket for the speedometer drive gear unit. We then slide the unit into the transmission and install the screw. Using the main shaft, we rotate the transmission to ensure the smooth operation of the speedometer drive gear. On some of the later Model 4 speeds, the speedometer drive gear has been relocated to the front wheel. In this case, the hole for the speedometer drive unit must be plugged. These metal plates are inexpensive and easy to install. Next, we install the main drive gear spacer key, or L key. Notice that this key has a short side and a long side. Before installing it, we must make sure that the notch in the main drive gear spacer is aligned with one of the splines in the main drive gear. Now we insert the spacer key with the long side facing in. The main drive gear sprocket has a flat surface on one side. Depending on the year of the sprocket, it may have a dished side. The dished side always faces in. We slide the sprocket onto the splines of the main drive gear until it is setting flush against the main drive gear spacer. Next, we install the lock washer and the sprocket nut. Remember, the threads on the main drive gear are left-hand threads, meaning we must turn the sprocket nut counterclockwise to install it. Before tightening the sprocket nut, we must once again lock the gears in the transmission to keep the main shaft from rotating. We slide our socket over the shaft and onto the sprocket nut. Using a 1/2-inch drive torque wrench, we torque the sprocket nut from 140 to 150 foot-pounds. Using a punch or a chisel, we flatten the tab on the lock washer. Once we have the shift forks adjusted properly, we place a new gasket on the transmission case. Next, we must rotate the shifter drum on the ratchet cover into the neutral position. Now, to place the transmission in neutral, we center our main shaft and counter shaft shift clutches between the gears. Before installing the ratchet cover, make sure that the two shift fork rollers are installed. Now, we put the ratchet cover in position on the transmission and tap it lightly in place with a soft blow hammer. Next, we put the ratchet cover screws in place, making sure that the vented screw is placed on the kicker side just next to the dowel pin. Using a 5/32 Allen socket, we tighten the 12 cover screws. For the final testing of the 4-speed transmission, we will be shifting through the gears to ensure the smooth operation of the completed assembly. If not already installed, we place the sprocket on the main drive gear. When the transmission is in the neutral position, the main shaft and main drive gear are able to move independently of one another. By pulling the shift mechanism up one click, we are shifting from neutral to first gear. You may find that the shifting is difficult. To alleviate this problem, we rotate the sprocket back and forth until the gear engages. It is normal to have some difficulty in shifting during a bench test. To confirm that we are actually in gear, we rotate the sprocket and verify that both the main drive gear and main shaft are locked together and are rotating simultaneously. Remember, the shift clutches are designed to engage each gear at engine idle speed or higher. Now, to get back to neutral, we push the shift arm down one click. By pushing the shift arm down again, we switch the transmission into second gear. The next notch we come to is third gear, and the last position is, of course, fourth gear. Now, we simply reverse the procedure, except this time we are pulling the shift lever up. The first click is third gear. The next click is second gear. This last click will miss neutral and bring us back to first. Now, to find neutral again, we once again push down on the shift lever. We then check to see if the main drive gear and main shaft are free to move in opposite directions.